I was thinking about Zeno's paradox again, Achilles and the tortoise. How can he possibly reach the tortoise if he has to cover this, like infinite number of smaller and smaller gaps?
Yeah, it's a classic. And it really gets to the heart of what we're diving into today.
Right, this idea of adding up infinite things but getting a finite answer.
Exactly. We're looking at the difference between a sequence and a series. They sound similar. People mix them up all the time, but they're fundamentally different beasts, especially when infinity gets involved.
Okay, let's unpack that. So, a sequence. That's just the list itself, isn't it? Like an ordered list.
Precisely. Order matters.
Hmm.
Think M-A-R-Y. That's a finite sequence.
Or like the Fibonacci numbers, 0, 1, 1, 2, 3, 5, going on forever. That's an infinite sequence.
Perfect example. Formally, you can think of it as a function, mapping each position number, the index n, to the term in that position n. It's just the ordered set of items.
Got it. Just the list. So then, what makes a series different?
Well, the series is what happens when you try to add up all the terms in that sequence. So instead of just listing A1, A2, A3, you're thinking about A1 plus A2 plus A3 plus forever. That's the series, often written with that sigma notation at Cayley.
Okay, but hold on. How do we actually do that infinite addition? How do we know if it even, lands somewhere specific, like Achilles finishing the race?
That's a million-dollar question.
Hmm.
And the answer lies in something called partial sums.
Partial sums.
Yeah. Since we can't literally add forever, we look at the sum of just the first n terms. We call that Sn. So S1 is just A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, and so on.
Ah, okay. So you create a new sequence made up of these running totals.
Exactly. You create the sequence of partial sums, S1, S2, S3. And here's the key. The original infinite series is said to converge to a finite value only if this sequence of partial sums approaches a specific finite limit.
So it all hinges on whether that sequence of totals settles down somewhere?
Precisely. If the sequence of partial sums just keeps growing indefinitely or bounces around without settling, then the series diverges, like the harmonic series, 1 plus 12 plus 13 plus 14. The terms get smaller, but the sum actually grows forever. It diverges.
Okay, but what about one that does work, like the Zeno one?
Right. Think about the geometric series, 1 plus 12 plus 14 plus 18 plus 18. The partial sums are 1, then 1.5, then 1.75, then 1.875. You see they're getting closer and closer to 2.
Ah, okay. The sequence of partial sums converges to 2, so the infinite series sums to 2.
You got it. That's how infinite steps can cover a finite distance.
But here's something that always felt a bit dangerous. With a normal finite sum, you can add numbers in any order, right? Commutativity. 2 plus 3 is the same as 3 plus 2.
Absolutely. But with infinite series,
Hmm.
that's where things get really weird and counterintuitive. That property can completely break down.
Wait, really? The order matters?
For certain types of series, yes. Specifically for ones that are called conditionally convergent. This means the series adds up to a finite number, but only because the positive and negative terms are sort of balancing each other out just right.
Okay. Like what?
The classic example is the alternating harmonic series.
Right.
1, 12 plus 13, 14 plus 15. It actually converges to a specific value, the natural logarithm of 2.
Right.
But because it's conditionally convergent, if you start rearranging the terms, say, taking 2 positive terms and 1 negative, then 2 positive, 1 negative, and so on, you can actually make the series add up to a completely different number. Or even make it diverge.
No way! Just by changing the order. So, like, rearranging the list fundamentally changes the final sum.
It does. It shows how careful you have to be when dealing with infinity.
Yeah.
The structure, the order, it becomes absolutely critical.
Wow. That idea of structure and order being critical, it applies everywhere, doesn't it? Not just math, but business, strategy, anywhere you've got complex systems. Speaking of navigating complexity, this deep dive is sponsored by Embersilk. If you need a hand figuring out AI, maybe for education or integrating it into your business or even just your daily life, you should check them out at embersilk.com.
So yeah, to wrap it up, the sequence is the list, the series is the sum. And when that sum is infinite, you have to watch the sequence of partial sums.
And the order can mess everything up if you're not careful.
Especially with those conditionally convergent series, it highlights how infinity doesn't always play by our finite rules.
So it makes you wonder, doesn't it, if our mathematical models of reality, like motion, rely on these infinite sums, and the outcome of those sums can depend so much on the order. What does that really imply about the physical world itself? Does Achilles have to take those steps in that exact order to guarantee he reaches the tortoise? Something to think about. Anyway, if you enjoyed this deep dive, please do subscribe to the show. And hey, if you could leave us a 5-star review, that would be amazing. It really helps get the word out. Thanks for tuning in.